میخوایی یه چکی بکن رو لپتاپه. Hey.
Hello.
Where do you want them? Oh, great.
I actually wanted to put on the front door, on both doors.
Okay, I'll turn it.
Thank you.
Hey, how are you?
Okay.
Do you need a different computer to set up the
Oh,
that's
yeah,
cool.
because okay, that doesn't look mirrored to me. Does it?
You need a different computer to set up oh, that's doesn't look mirrored. What's that noise?
That's actually because it's going recursive.
Oh, it's like has a buffer or it's just recording?
Yeah, this one is recording and this one is playing and it just loops. Yeah. Okay, just close this. Try to download Sunjoy. Let's see.
Do you want to maybe open the door with this?
Yeah, I think so. It should be okay.
It might be that better to put it someplace here or here so we can keep the door open.
Yeah. Okay.
It doesn't work on the TV. Nothing.
Or you can even do it on this glass.
Here.
Okay, I'm ready.
Sure. Tamam, teşekkür ederim. Oh, really? I also enjoyed it. Thanks for coming. I'm in Kaleti too, actually. 4004. Yeah, I couldn't book the large conference room in the computer science, so it's already booked. He was nice. How's it going in Berkeley? Oh, cool.
Yeah, there's like 40 or 50 people here, and we're all like doing some pretty intense research.
Nice. Cool.
So you're going to start in a few minutes, so should I just mute it and
Yeah, sounds good.
then I'll also turn off the video, but I'll be able to see you. Is that right?
Sounds good. Yes, I think so. You can just click on the camera. Yeah.
Or I guess I just need to mute it. I don't need to do the other. Anyway. And so you're gonna go for about an hour?
Yeah, I try to finish in like 45 minutes. I aim at 45 minutes to finish in 45 minutes. So hopefully it'll be less than an hour.
And you got the forms and all that, right?
Yes, yes. Thank you. Thanks for sending those. Thank you so much. I was emailing like you like every day. I was worried about that. Yeah. Thanks for sending them. Thank you. Okay, I got the forms. Actually, see if you can see the screen. Can you see the slides now?
Yeah, I can see the slides.
Okay, sounds good. Thanks.
Same room.
Hey, Gary. Thanks for coming.
You have your paperwork. That's good. Pancho didn't have his paperwork.
Oh, really?
Yeah, because it was in my box, and I didn't know it was going to be. I told Pancho people didn't always do this, and you're like going.
Being a good primatologist.
Are these both calf?
I think both of them are not non-decaf.
Yeah, both are.
Yeah, they just have different colors.
Hey,
You don't have to sit all the way back there.
Good. And you were here.
I'm only here briefly.
Crash the seminar.
Thanks for coming. Thank you
Hey,
so much. Hey.
She came all the way from Australia just to see.
Yeah.
Just for your seminar.
Thank you.
Well, you're right in the way. So we have some committee members too, right?
I think so.
Is
Sanjay is
Javier-
here. Sanjay is online.
Okay, is Javier still on your committee or?
Javier?
Yeah,
No.
okay, so it's me, Sanjoy,
Lawrence, Juvan, and Nuno.
Nuno is always late. Jenny said she might come.
What was that?
Yesterday at Punch's Defense, it sounded like Jenny might come. I'm not sure.
Yeah, I think she wanted to come today too. Well, actually, no, Andrea. What's the other door actually?
Yeah, but this is the one that says 4004.
Yeah.
It's a bit confusing. He wants to show this.
I did that too. You don't have to be embarrassed.
Thank you for coming. Thanks.
Yeah, sorry.
It's too late. Lose track.
So many.
Okay, that's where the party is tonight. I had another PhD yesterday, so.
You're cranking them out.
Have to. Let's see, so we're waiting for Nuno and,
So
Just
just
Nuno.
Nuno, yeah.
okay.
This was it fun?
Okay, so let's get started because Nuno's always late and it's 5 minutes after. So I'm very happy to, well, happy and sad to be introducing Mohsen as our PhD candidate today. I was very lucky that I wanted Mohsen to come to UCSD, but I didn't have the funds because I read his connection science paper and it was about things I cared about. And then I really lucked out because his advisor, who was one of Javier Mavellan's star students, Ian Fazel, decided to come to UCSD and Mohsen with him. And so I got to work with him anyway. So that was really good. And today Mohsen's going to talk about perceptual algorithms for social robots in early childhood education. So take it away.
Thank you so
Mohsen.
much. Thank you all for being here. Today I'll present my thesis, Perceptual Algorithms for Social Robots in Early Childhood Education. So social robots are becoming actually very widespread in the classroom. And there are so many labs that do put a robot in the classroom and try to teach kids and try to monitor them. So children are very eager actually to engage interaction with the robot. So that's actually very promising. And robots can monitor children's behavior in an automated way, in a way that teachers actually can't do because they're very busy. So more specifically, I have done my PhD in the context of Ruby project, and this is a project that started in 2004. Javier was actually a pioneer in putting robots in the classroom for children. So this started in 2004 with the goal of providing equal learning opportunities in early childhood education. And the goal for Ruby was to be a very low-cost teacher's helper that can be replicated 1,000 times. Also, we just did like 6 robots. But Ruby in the classroom can learn from the kids, can monitor their activities, and can teach them different materials.
It seems like he's trying to attack you.
She's fun. She hasn't seen me in a while, so she's like, too.
Okay, that's
Yeah. So here's an example, like 3 typical behavior that Ruby does in the classroom. The first one is sing and dance. When Ruby sings and dances, and the kid make kids happy. Increase the volume. It's not too loud for some reason. So usually kids gather around Ruby in the classroom. We put it in a corner, and there are like 5 or 10 kids around. The next thing is vocabulary, but Ruby shows a picture of a cowboy and says cowboy, for example. And kids are supposed to learn the names of the images or the objects. And then the third one is the give and take, which is very tricky, but kids usually put a toy in Ruby's gripper, and Ruby grabs it and then looks at it and then says the name of the toy. And the kid is very happy because he could do it after like so many trials. So over the 13 years of the Ruby project, there has been 6 different robots, and each one with a different set of perceptual primitives. So Ruby 1 and 2 were equipped with face detection and facial expression recognition that allowed them to analyze the one-to-one interaction with the kids. Ruby 3 and Ruby 4 had mood detection and cry detection, which allowed them to act consistently with what is already going on in the classroom. For example, not to make a noise. I think somebody needs to open the door. Not to make a noise when the teacher is talking, or then, for example, a kid is crying, not to make extra noise in the classroom. So I joined the project in 2012, and I worked solely on Ruby 5 and Ruby 6. And what I did is I added face recognition perceptual primitive to Ruby 5, and then I added active object recognition to Ruby 6. So there are 2 major parts in my thesis. The first part is the face recognition, but we published early in 2013 and 2014. And the second part is about active object recognition, which is the bulk of my thesis, and we published in 2015, 16, and 17. So I start with the face recognition, which was published in ICCD workshop in 2013 and the human-robot interaction workshop in 2014. So the primary goal is to show that in the Ruby project is to show that Ruby is actually an effective teaching technology. And the previous work in 2008, Javier showed that actually Ruby can increase the vocabulary of the children with the sustained interaction. But to publish that result is required them to analyze the videos manually, going over hours and hours of video recorded in the classroom, which took them 2 years. So there was certainly a need for automatic face recognition. And that's what I did. I joined the project in 2012, and I developed the classic computer vision pipeline. This was almost at the same time as the rise of the AlexNet and deep learning. So I did classic. That was more common in those years. So the first thing we did is we collected a data set of faces. We let Ruby run in the classroom for 6 months and collect images of children. And the total of 7,000 face images was collected and manually labeled of 16 toddlers and 12 adults. And the faces exhibit a variety of facial expressions, orientations, and also they have a temporal evolution component. So here's the classic computer vision pipeline that I developed. It's a special pyramid followed by patch extraction, and then feature extraction of those patches, and then classification. So for the test set, we temporally sorted images for each subject and used the last 30% as the test set. And the best result that we got was 84% with the fusion of all features, the HOG, LBP, and the DAISY features. So here's an example application of face recognition. This is a sociogram. We call it Rubygram. It shows the social structure of the classroom. It actually shows the preference of children to play together in front of Ruby. And the red links means that they prefer to play together, and the blue links means they try to avoid each other, kind of. And this sort of information is actually very useful for teachers. Teachers really like this, and with the automatic face recognition, generation of something like this, such a report, becomes very easy and automatic.
Is that kid in the left autistic?
A little
Not
bit.
connected to anyone.
As teachers are very careful of saying things like that about good kids, so it's really hard to say. Another thing we did with the facial expression recognition primitive is that we try to predict the preference of children over different activities. So we'll ask teachers to rank the activities in the classroom based on the children's preference, and then Ruby tried to predict that order using different emotional channels, using 6 actually different emotional channels, and we found that actually happiness is has a statistically significant correlation with the teacher's prediction. It actually correlated with teachers more than they correlate with each other. And here's another example of facial expression recognition. We averaged all the occurrences of the bus song, and this is the level of happiness in the classroom over like 25 occurrences of this song. And we can see these peaks in happiness when it says all through the town, and that's interesting. And there's a large peak at the end. That's perhaps when adults are happy that the song is finishing. So these two were basically the primary works that we did in early couple of years. We collected a data set of faces over 6 months. I developed a classic computer vision pipeline. We showed Rubygram, which is an example usage of face recognition in the analysis of the social structure of the classroom. And we saw example applications of facial expression recognition for monitoring the temporal evolution of happiness and to predict the preference of children over different activities.
Did you revisit these data sets using CNN-based approaches?
Using what?
CNN-based.
Oh, no, actually.
Because for face recognition, I assume probably you can achieve 99.9
Yes,
something.
yes.
For expression,
correct.
90%, I assume.
Yeah, that's correct. I always thought that CNN will do a good job on this data set. Well, it's actually really challenging because some of the kids' faces change over 6 months so much. I actually was manually labeling them, and I thought that there was just one kid, and I thought they were 2 kids, and labeled them as 2 different kids.
Yeah.
And teachers saw that and said, okay, these are the same kids. So the aging is there, the facial expression variation is there, the lighting, and there are 3 different cameras and for 3 different. So there's a lot of challenging things, but CNN, I think, will.
Yeah, nowadays it's not a challenge at all. It's so easy.
Yeah, that's
almost
right.
like a piece
These
of-
are yeah, that's right. I never tried actually CNN. I was interested to do that, but I guess there were other priorities in the project that I had to move on with those.
My photo recognized my Boy Scout picture. No problem.
I think there are a couple of recent shows, like they were able to identify twins, one out of many, and outperform humans in a real challenge. All these things, I think, what you're saying, like shadow,
Yeah.
just these are just
Just
so minor.
face recognition is
Yeah.
pretty mature
Yeah.
now. There's so many people working on it, and I think it's pretty mature now. Okay, so moving to the second part, which is on active object recognition, we published we published germs in 2015 in British Machine Vision Conference. We published the joint label and action prediction in the Journal of Computer Vision and Image Understanding, and then in 2017 I published the last work. It's actually not published, it's under review in IROS 2017. So going to the first work, in active object recognition is it's called GERMS, a data set for active object recognition. So the whole active object recognition was motivated by the popularity of give and take. So usually kids bring a toy and put it in his arm, and Ruby grabs it and looks at it.
What's this?
And usually says the name of the object, and there's an opportunity to teach the object names to the kids. And there's actually another opportunity to compare the 3D in-hand object learning for the kids versus the usual way that Ruby does it, which is showing a 2D picture of the object on the below screen and saying the name. So there's an opportunity to compare these two learning paradigms. So when Ruby grabs an object, it has actually an extra degree of freedom in controlling the viewpoint of the object. And active object recognition is about controlling that degree of freedom to achieve a higher recognition accuracy, and achieving that higher accuracy with fewer number of views per object. So I have reviewed the existing active object recognition approaches in my thesis. I just briefly mentioned their common theme or common properties. The first thing is that they usually require a generative model of objects. That is, when they want to decide what to do, they need a generative model to see the effect of different actions. They usually look just for the best next action, which is a greedy approach, which is not optimal in the long time. And they're computationally expensive because the action selection is posed as an online planning problem. And then they usually test on toy data sets, which are not publicly available, which makes comparison between different approaches very difficult. And what we did is actually in this work, and the purpose of the next two works is that we don't require a generative model of objects. We use Q-learning, which looks beyond just the next action to learn object exploration. We do a single pass through the neural network at the test time, which is pretty efficient compared to an online planning paradigm. And then we published GERMS, which we hope to become a standard data set for active object recognition, and we tested on the GERMS data. So here are images of GERMS. Here are images of GEMS. We actually 136 different objects like these. We bought them all together. They come in a very large box. There's a company, Giant Micro, that makes these. And we selected these because we wanted to minimize the effect of children's prior knowledge on object learning task. So these are the objects that kids most likely don't know the name of. And we put each object 10 times in Ruby's gripper, and it grabbed it and rotated it and collected a video. And out of those 10 views, 6 of them are used for training and 4 are used for testing. Here's a comparison between the GERMS and the data sets that they use in the literature. And we can see that GERMS actually have more objects. It has more views per object. It's publicly available. It has occlusion of the object. It makes it challenging, and it has a complex background. Again, makes it a challenging data set.
So what's the size of the data set altogether?
136 different objects.
But how many images?
Oh, and the images, 120,000 images. Because we collected videos densely, there are actually a lot of images. So here are example subsets of toys. The top row is the daddy neuron, the graduation neuron, and the ordinary pupil neuron. And the bottom is the cancer, prostate cancer, and the breast cancer. And recognizing these toys actually require the robot to recognize from very fine-grained visual properties like the color of the ribbon. And if it grabs it from the back, it has to rotate them and see the front and then recognize the object. So it's actually a good data set for active object recognition. So we approached, in this early work, we approached active object recognition as a Markov decision process. And Markov decision process is composed of states, which is actually the belief of our objects. At each time step, we have a belief of what this object in the hand is. We can perform a set of actions on those objects to change the beliefs. There's a transition function that delineates the transition between beliefs as a result of actions and the environment properties. And there is a reward and a discount factor visual in that we want to do recognition as quick as possible. So the goal is to find a policy to recognize the object, to actually inspect the object and recognize it as fast as possible. And we approached this problem using Q-learning. And the thing is that we don't have the ground truth policies for object inspection, so we have to discover those. And Q-learning does require minimal supervision with just a reward. There's an environment, which is actually the toy and the robot's gripper, and there's an state, which is the current view of the object, and there's a reward, which is proportional to the accuracy of object recognition. There's action value learner, which tries to predict, which tries to learn the best actions to explore objects, and then selects an action to change the view of the object. And the way we did is that we modeled the action value learner using a neural network that as input receives beliefs over object, the current belief over object, and it predicts action values. How good are these actions, different actions in exploring the object? So here's the overall architecture of the neural network, the model that we used. The early stages are fixed, the 7-layer AlexNet pre-trained on ImageNet, and we didn't learn that during action value learning. The second part is composed of 3 fully connected layers, followed by softmax. The reward in the Q-learning to train this network is proportional to the confidence in the correct object label. And then there is the belief accumulation concept, which is if you have multiple views of the object, how do you combine those evidence to reach the final belief? And the way that usually is done in the literature is using naive Bayes, where you have 2 belief vectors, you element-wise multiply them, and then normalize, you reach a new belief vector. So we trained the neural network. Here's the accuracy on the test set for the left and the right arm. The red curve is actually the policy trained with Q-learning. The green one is the policy, the random policy, where it just randomly picks a set of actions. And then the blue one, which is the worst one, is the sequential. When you start from one view and then go to the next immediate one and then continue like that. You can see that the Q-learning actually saturates in performance in less than 10 actions, while the green curve actually gradually increases. Here is the results in a tabular format. It shows the number of actions, the number of views to reach the same level of accuracy for these 3 policies. And you can see that deep Q-learning reaches the same policy with significantly lower number of views required. So in summary, we published germs. We hope that it becomes a standard data set for active object recognition. It's actually pretty challenging. We published the baseline results using deep Q-learning, the baseline active object recognition results, and then we saw that the deep Q-learning saturates in performance after less than 10 actions. That's pretty fast. It just reaches the best performance. Okay, so I'll move to the second part of active object recognition, which is the joint label and action prediction. And the basic motivation here was that can we train a neural network to simultaneously learn the appearance of the object and learn to predict the actions to be performed on the object, to recognize the object. And this whole simultaneous training reduces the training time of the neural network. The development of this work, we developed a new belief accumulation technique based on Dirichlet distribution I'll describe later. So here's the gist of actually what we did here. We proposed a neural network model that as input receives an image of the object. In the middle, it calculates the belief over different object labels. And at the end, it calculates the action to be performed on this current view to increase the accuracy of recognition. And then the state encoding, the belief accumulation is actually a novel thing that we did here. So I talked about naive Bayes. When we have multiple views of object and we have multiple beliefs, how to combine those to reach a single accumulated belief. And the usual way that active object recognition people do that is naive Bayes. You just multiply them element-wise and normalize and reach a new belief. We found that to be actually very overfitting to the training data. And that's because of the element-wise multiplication. Another thing that actually an alternative that we proposed is based on Dirichlet. So we modeled the observed beliefs per object action pair using a Dirichlet distribution. So Dirichlet is a natural way to model a distribution over beliefs. And for each object action pair, we fit a new distribution. And this way, we are actually using the action information to disentangle the state representation, that belief accumulation that is going on. The use of action actually disentangles that. So here's the overall architecture of the neural networks. It starts with 3 convolution layers, 3 fully connected layers to predict the label somewhere in the middle. It predicts the label, the current belief over objects using the current view. The second part is the action value prediction. It's almost the same as the previous work, but now it's on top of a neural network that is learned end to end. And you see that there's the Dirichlet layer before the action value learning that combines the current belief and the previously observed belief to reach to encode the state. And the thing is that the error is backpropagated all the way to the convolution layers from the action value learning. It means that you're learning the visual features based on the action value error, actually. So the cost to train this neural network is of the single image classification, the action value learning, which is coming from the Q-learning, and then the negative log likelihood for the Dirichlet distributions for each object action pair. So here is the comparison on the performance of active object recognition. The x-axis is the number of actions performed, the number of views of the objects observed. The blue curve is the distribution. There's the neural network trained with Dirichlet distribution. And then the red curve is the naive Bayes approach. And you can see there's a significant difference in performance between the Dirichlet and the naive Bayes. So what happens here is that the naive Bayes actually underexplores the training set, because there's a view of the object that goes into neural network and it selects the next view that trains the neural network. And because the naive Bayes overfits to subset of actions, it only underexplores the training set. Therefore, the performance actually significantly drops. On the other hand, the Dirichlet is actually doing much better. So that the dashed line represents the random policy on top of that network. And then the solid line is actually the deep Q-learning, the Q-learning learn policy. And we can see for naive Bayes, the Q-learning is doing better than random, but for Dirichlet is actually not doing better than random after action, the second action. So that's actually a general trend that I observed. When the baseline of the accuracy increases, the random policy becomes very good, and it becomes very hard to beat using deep Q-learning.
So you know what would be like the performance if you just train the classifier of all these images? What would be like the sort of, I guess that would be
yes,
about
I actually have that in the paper and published it. It fits somewhere in here. So it's below the Dirichlet learning. It means that Dirichlet actually selects images smartly to train the neural network. It selects the images that are more useful for classification. As a result, the performance actually increases slightly.
But the Dirichlet model also is very sensitive to this hyperparameter. You have to carefully search for this kind of
Yes. So it has a prior. I actually used the uniform prior over the Dirichlet parameters, and that actually turned out to be good. But since it's learned using the maximum likelihood approach, it's actually a good fit at the end. So it's not that bad. If you look at the curve of the negative log likelihood, it's actually decreasing. It means that it's learning pretty good. So I went one step further because the random policy was doing better than deep Q learning. I actually forced the neural network to visit all the actions at the training time on top of Dirichlet. So Dirichlet visits some of the actions, but perhaps it's not visiting all of them. It selects. It's kind of biased towards some actions, and also this leads to at the test time being overfit to a specific views of objects and the specific actions. That causes the random policy to be better after action 3, 4, 5. So I forced this exploration of all actions at the training time. And that green curve, the solid line, is the policy with the non-duplicates, hard-coded in the training time, and you can see that they're doing better than the green dashed curve, which is the random policy on top of that. So directly works. It definitely works over naive Bayes. Is much better than naive Bayes, but still there is this overfitting component that I have to hard code some criteria to overcome. So here's the results in the tabular format for different actions. You can see naive Bayes is the red, Dirichlet with repeated visits at the training time is the blue, and then Dirichlet with no duplicate visits is the green. And you can see that the Dirichlet with non-duplicates actually removed at the training time is doing better in almost all cases except for 2 cases. The other 2 cases are Dirichlet with repeated visits.
So those columns are the number of views?
Yes, yes. So each it shows that how many views they have selected. So here's actually a visualization of the policy. Each row is an action, rotation inward or outward with different magnitudes. So that the larger the arrow, the larger the amount of rotation. And then here you see the naive Bayes actually bounces between this large rotation outward and then goes to this large rotation inward and then just bounces between those two. So it kind of finds that to be a good policy, but it's only a local minima. On the other hand, the Dirichlet with no duplicates at the training time actually explores a whole set of actions, which leads to better performance at the test time. Okay, so in summary, we propose a neural network to jointly predict the actions and the object label at the same time. We trained it using stochastic gradient descent for all the layers end-to-end. We proposed a Dirichlet generative model for state encoding, which was better than naive Bayes. And we saw that resulted in higher recognition accuracy.
So in the end, what's working was really Dirichlet plus. It's in the end, it's a
Plus
mixture of
the hard-coded, yes.
Hard-coded.
Yes.
You enforce some randomness, so you will do no harm. At least you're going to be better than random, because in general, you're saying with enough
Yes.
actions, randomness
Yes,
actually
yes.
wins over. Then you have randomness plus some Dirichlet kind of more
Yes, that's
targeted kind
yes.
of actions.
Yes. So
Yeah, you can think of that no repeats as inhibition of return, which we see in humans.
Do you have any bounds there?
anyone?
Bounds to prove?
Oh, on this work at the Q-learning, no, actually, because it's when the neural network is very much in the local minima, and then when Q-learning is on top of neural network, it really becomes something messy, you know, that you hope that to sit down on a good policy, but it's very difficult, you know, when you combine both of them together. So that's actually the motivation for part 3, which is the belief tree search for active object recognition. So again, the main motivation for this work was my frustration with the Q-learning and the neural networks. So we don't have a good policy, and we hope that the Q-learning will learn something, and there isn't much that we can do. So I said, okay.
Did you ever try policy gradient methods?
Yes. So this work actually has the policy gradient method. So can we train active object recognition in a supervised way? Can we discover a set of policies on the training set that have some guarantee on the optimality, and then we learn those in a supervised manner, and then transfer that knowledge into the test set? And what we ended up is this work, and as a result of formulation, it allowed me to actually systematically model the appearance of the object. So
She's getting bored.
yeah, she's grabbing me from behind. So in previous work, I just trained a neural network end-to-end with appearance and action value learning, and I hope that they could be done together and it worked. But this work actually is a systematic approach to modeling the object appearance and the learning of action values. So in this work, I modeled the active object recognition as a POM-DP problem, partially observable Markov decision process. And what we have here is a set of states which are the object labels and not actually the object beliefs. So there are 136 different objects, 136 different states. There's a set of actions, again, as the previous one, that explore different views of the objects. There's something new over the MDP, which is the observation, which are the images. So at each point in time, we observe the images. We don't see the identity of the object. So we don't observe the state directly. We only see an image, which is an indicator of it. There's a transition function, again, the same as before. It just denotes the transition between the views of the object and the resulting belief. Again, we have another new component over Markov decision process, which is the observation function. And observation function tells us the relation between the images and the object labels. And then there's the reward and the discount factor as before. So observation function actually gives us the likelihood of images for different object labels. So I modeled the active object recognition as a POM-DP problem, and then I approached it using belief tree search. That's so funny. So belief tree search is actually a search method in the POM-DP in the belief space to discover a good policy or a good value or good action value for POM-DP problem. So there's a rich actual literature on the belief tree search, but I adopted one specific algorithm that met my requirements, which was to be computationally bound, and because of my observational space is pretty large, it has desirable properties that allow my problem to be manageable in order to find a good policy. So the belief tree search actually acts like this. It starts with a root belief, which is the current view of the object. It performs a depth-first search, just performs a set of exploring actions, and goes and reaches a leaf where a reward is given. The reward is proportional to the accuracy of object recognition. So when the reward is reached, we backtrack the reward and update all the values of the nodes in the middle. And we repeat this until all actions in the tree are explored. So it's pretty much exploring every actions, but it packs similar beliefs together to decrease the search space. So the search space is the belief space is an infinite space. It just packs the similar beliefs together to make the search manageable. So after all, what we get for the root is a value, and that value has some guarantee over optimality. So it's within some error value of the optimal value. And there is a set of corresponding action values for that belief. So given each belief, it gives us the value of different actions for that specific view. So we extract all these values and action values using belief tree search for every view of the data set on the training set. And now the problem is, how do we transfer this knowledge from the training set to the test set? And there are three different approaches that we compare in this work. The guided actor critic, the guided neurally fitted Q-learning, basically that's similar to the Q-learning that we did in the previous two works. The guided actor critic is a policy learning method. Both of the first ones are reinforcement learning based. So we guide them using the belief tree search policy. So there's no direct way of forcing them to learn the policy. We can just guide them to learn good values. And the third approach is the supervised learning of the policy using LSTM network. So here's the schematic of the guided actor critic. So in the actor critic, there's an environment. Again, it provides the current view and the reward for active object recognition. There is a policy learner, which is a neural network that maps the object belief to different action probabilities. And there is an auxiliary component, which is the value predictor, which predicts how much valuable is the current view. And that value predictor helps the policy in the process of learning a good object exploration. And the way that we guide this is that the action from the policy is discarded, and instead we plug in the guiding policy from the belief tree search. So it's like you learn your internal representation using the actions that somebody else selecting for you. So you're just observing the things that they do, and you update your internal representation too. So that guiding policy is something that comes from the belief tree research. So it's a policy with some optimality guarantee. And here is the performance averaged over both arms. The x-axis is the number of actions performed. The y-axis is the accuracy. And it's actually the random policy, just selecting random actions, and the actor-critic plane with no guiding perform exactly the same. The only thing is that the actor-critic has a large variance. So the policies that it learned sometimes are good, sometimes are actually very bad. But that variance is something that we don't want. The guiding process actually helps the actor-critic method in this one, and in this one, the yellow curve is doing slightly better. So it helps a bit, but again, the variance is pretty large. The second approach is the guided neurally fitted Q iteration, basically the Q learning from the previous work with some extension. And again, the action value learner is a neural network that maps the current object belief to an action to be performed on the object. And the way that we guide it is that we just plug in the guiding policy and let that drive the exploration. And here you can see comparison. Again, neural fitted Q learning, the plain Q learning and the random policy match exactly the same almost, but the Q learning has a large variance. And when guiding it, it actually helps a bit in here. You see there's a bit of difference in the guided and the plain version, but the guided version again has some large variance, which is not desirable. So the third approach is actually the supervised policy learning. So we have all these good policies on the training set. We drive some rollouts. Basically, for each view, we select a set of actions based on those optimal or near optimal policies, and then train that to a LSTM. So LSTM sees a bunch of views of objects or current belief of those views, and then tries to predict the next action to be performed on the object. And we found that actually doing LSTM is critical, because if you just simply map using supervised learning of belief to the action, does not work. And here's the comparison between the random and LSTM. First thing is that the variance is very low. So the variance is very low, that's pretty good. And then the red curve, the LSTM is doing significantly better than random in these earlier stages. At the fifth step, where everything has been, almost all the evidence has been accumulated, there is not much difference between different methods. And here is all the approaches together. Again, the top approach is the supervised LSTM approach, and the other three almost doing the same level of performance. Another thing we did is that we generalized this to novel objects. So we trained the object exploration using a subset of objects of the germs, and then tested on another subset. So it's like you learn to explore objects in general and transfer that knowledge to unseen to novel objects. And you can see random, the purple curve, is doing much worse than LSTM. LSTM is doing much better. And it shows that actually generalization to novel object actually works.
So what is the price to have more actions? So if you expand the axis, let's say to 10.
Yes. So yeah, it's actually starting to flatten in here. So there's not much. You don't gain much.
So if you are able to afford, let's say, 10 actions,
yes.
So then, so all these benefits from LSTM start to diminish. Right?
Yes. So the goal is to actually do the recognition of the first 2 or 3 actions as fast as possible. If you are able to process as many images as possible offline, yeah, that's fine. You just can accumulate all the evidence. But at the training time, when Ruby is in the classroom and just rotating the object and trying to say the name, the real-time interaction requires actually to be pretty quick and say the name of the object as fast as possible.
Can you explain how you know what the answer is if the object is new?
So the object is new means that the belief, the visual appearance learning has been trained on all the objects. It's just the exploration of the object that is new, that is generalization. So it's just learning to explore objects in general. And so the last part that we did in this is to improve the observation function. So observation function is the likelihood of image of the image for each object labeled. So it says that how likely is this current view for different objects. And we usually define a model for likelihood and fit it to the data using maximum likelihood estimation, and that's it. So the likelihood function is actually an approximation. In the regular PMDP, usually the observation function is given and fixed and ground truth. But in our case, observation function is only known approximately. So we can improve that. And the PMDP formulation allows us to actually drive a formula to improve observation function to increase the reward of active object recognition. And the derivation of formula is in the thesis, but just the short version is shown here. It shows that it boils down to a weighted retraining of the likelihood, where for each view, the weight is corresponding to how much valuable it is for active object recognition, multiplied by how often that view is likely to be encountered. So if that's a good view, it has a high value, and a good policy usually tends to go to that view. So its weight will be larger. If it's a bad view that is not distinguishing between different objects, it will get a lower weight. And then in the retraining, where the visual features are learned, that view or that image gets a lower value. So we retrained the observation function, and then we redid the LSTM network, and that's the blue curve. So the red curve is from the previous graph, and this blue curve is after learning the observation function and then doing LSTM. And you can see that the performance significantly improves. The baseline, which is the action 0, actually improved. It means that it learned the appearance of objects better with the weighted version. So we can iterate this process. We just do another retraining of the observation function and another retraining of the LSTM, and that is the green curve. After iteration 3, it still gets better results than the previous one, but it's only slightly better. And then after that, it starts to get worse, actually. It overfits to the data, to the training data. So in tabular format, the LSTM, after 2 times improving the observation function and training the LSTM network, performs better than the other ones, significantly better. So in summary of this work, we proposed belief tree search for extraction of good policies on the training set. We proposed a supervised framework for learning these policies and transferring this knowledge from the training to the test set. And we saw that actually iterative improvement of the observation function helps to increase the active object recognition accuracy. So with that said, I'll move to the thesis conclusion. Perceptual primitives for Ruby actually enable Ruby to enrich its interaction with kids, enrich its analysis of the social structure of the classroom, and it provides new learning opportunities for Ruby and for the children. So ideal of face recognition, actually face recognition for Ruby enables it to enrich its analysis of the social structure of the classroom. Facial expression recognition that we use enables Ruby to analyze the temporal evolution of emotion, temporal evolution of happiness over activities, and it allows Ruby to discover the children's preference over different activities. So the next part was active object recognition, which allows Ruby to teach 3D in-hand objects to kids, and it allows to compare learning on a screen versus in-hand objects. We saw that existing active object recognition actually lack a standard data set to compare their performance against each other. That's why we proposed GERMS, hope to become a standard data set for active object recognition. We saw that simultaneous learning of object appearance and action values is possible using the end-to-end neural network, end-to-end training of the neural network, and we saw that Dirichlet-based belief accumulation is actually a better alternative to naive Bayes. Reinforcement learning methods usually have difficulty when the baseline performance improves. So if your base single-shot image classifier is pretty good, reinforcement learning cannot do better than random. And that's why we move to supervised learning of policies. We extract some policies that have guarantee on the optimality and then learn those using some supervised machine learning technique. And then finally, we saw that the PalmDP formulation allows us to systematically model the object appearance and improve that modeling to increase the accuracy of active object recognition. So for future directions, I guess agent Ruby is something that we talked about a lot as social perceptual primitives for Ruby. That's when we put Ruby in the hallway of some library or some building and people gather around and talk with Ruby, actually interact socially, engage in interaction with Ruby, and Ruby can collect their data and analyze their social behavior. And that's something actually very interesting. We can put Ruby in different places in the campus and provide a cognitive map, like how much happiness is seen in different days in different places in the campus. And actually,
week.
Yeah. Another thing that we actually thought about a lot was semi-supervised person recognition. That is, you don't have to spend so much time on labeling faces, and it's just Ruby learns with minimal supervision, just asks from time to time from the teacher what's the label for this kid, and then automatically updates its internal data set. And then for active object recognition, the next step will be to do shift of attention inside an image. You just shift of attention, can help you recognize objects using shift of attention. And with the supervised approach or framework, that's become much easier. With the reinforcement learning, I thought about a lot, and it was actually a nightmare. And with the supervised approach, is much easier. Okay, so that was pretty much everything I wanted to say. So I just want to acknowledge, thanks Gary, so much my advisor, for helping me to finish my PhD. I want to thank Javier for starting the Ruby project and hiring me. I want to thank Deborah so much. Thank you so much for helping me over every stage of my PhD. I also want to thank my committee. Thank you so much for your time, for being here. I want to acknowledge Catherine Owen, Director of Early Childhood Education, and Lydia Morrison, the teacher in Classroom 1B. That's where we operated all these years. Without their help and support of the Ruby project, we couldn't do any of these. And I would like to thank Andrea Chibo for her support of the Ruby project, her support of me during my PhD, and also the fact that she adopted Ruby. She'll take care of Ruby after I'm gone. And I would like to thank NSF, FISP, and Temple Dynamics of Learning Center for supporting my PhD. I would like to thank Gary's unbelievable research unit. They always have to sit through my talks and give me feedback. I would like to thank the late Machine Perception Lab, which now is in Apple. I would like to thank Cality2 for providing that space and equipment for me and for the Ruby project. And there's so many friends and so many people that helped both me during my PhD and also helped the Ruby project, my fiance, and people in the MP Lab, the undergrads that helped in the Ruby project, and the people in Cality2, the multimedia group that provided computational resources, hardware resources, and also a golf cart that we could carry Ruby around and go to the classroom. And thank you so much for your attention and your time. These are the publications. Thanks.
Ruby's new dog. Ruby's got a pet.
Two, Irat and the dog.
Okay, questions from the Peanut Gallery? Visitors? Yeah.
For someone out of this field, that I have no idea what is machine learning. So how do you define accuracy, and how does Ruby understand that that's like after each different action? When is a good time for Ruby to tell them, like to say the name of the object?
Yeah. So actually, when it's a real-time interaction, it's pretty tricky. The timing is very tight. So when a kid brings a Ruby, if Ruby just delays in grabbing the object or saying the name of it, the interaction is disconnected. So Ruby could should do it actually as fast as possible. I can't say a time that like 10 milliseconds or 1 second, but it should do it as fast as possible. They lose interest if they don't get any response pretty quickly.
Very short attention span.
Yeah.
12 to 24 minutes.
But I guess the question is like, how does it know that it knows enough to give an answer?
Yes. So if it has certain level of confidence, there should be an answer. If it falls in the shady area, like less than 95%, then perhaps it's not a good idea to say the name, because if it's wrong, then we're messing with their knowledge and their wiring. So I think it should be pretty confident, more than 95%.
I could say something. We did talk about the possibility of putting the 4 top confidence levels and asking the kid again, is this? Because that's something that could happen naturally between people.
Yes.
Did I get the right thing? And that may shorten the time, but also have an opportunity for the kids to teach Ruby, for Ruby to teach the kids. But that, for it to actually work in the classroom, it's a lot of extra work.
Yes.
Is there a reason usually the left hand had better performance than right hand?
That's actually a property of the data division. It was like the artifact of the data that we had, because we recorded both arms, the different people, the different timing, and the different amount of data. And that was something that was systematically injected in the data set as a result of
I thought it was because Ruby was right-handed.
that also.
What is, I think, was 48, you talked about LSTM. You talked about using LSTM that gives you better accuracy. Is that because of the specific using LSTM, or you cannot get to the same accuracy with, I don't know, fully connected networks?
Yeah, so the supervised learning of policies. I tried different actually machine learning techniques, like from random forest to SVM to everything that you can think of. I tried them, and it was very surprising that it's not working. And only LSTM did actually a good job. I think that was because I was doing the rollouts. So it's kind of a sampling of those optimal policies. If you directly go and predict those action values.
Ruby's agreeing. She just
really on the green. So yeah, I think that's the property of rollout and LSTM being able to accumulate evidence over different views. But that was pretty critical.
If I could make one comment. Mohsen and I kind of joined the Ruby project about the same time. It was a very short time before Machine Perception Lab went off to do emotion. So we were kind of orphans in the lab. And there's a sense in which, for a lot of times, it was very frustrating because we didn't have the environment of the lab, we didn't have the history. Tried to get Javier to kind of look at the work. But what I witnessed kind of from the outside is that when deep learning started to come back, Mohsen got interested in it very quickly. But Javier was very resistant at the beginning. So that was a good side of being an orphan, because he was left on his own devices to develop it. Javier kind of realized that from his own experience how amazing it was. But it was really interesting to see the field kind of completely change from the first 2 years and the last 3 years, and to kind of see what it took to stay and catch up with it. So there was a group of people here that started a deep learning reading group, and I think they ended up being very supportive of what you're doing.
The other thing about your data set, have you tried to apply it to different cultures? Because one reason that you overfit so much probably is that you have just one group, so your model can fit it really quickly. But if you have different cultures, usually kids behave differently, so you have more space to fit in.
We're actually trying. Hey, you want to say something about it?
Yeah.
This is Mohsen's defense. We're building on version Ruby in Australia.
Do you see any kind of like really interesting results in terms of case?
We haven't got this far yet, but we're building a much simpler version and taking it to Indigenous communities. A very different distribution.
Yeah, but the basic idea was that we make thousands of Ruby and put them one in the classroom here in the USA and put one in a classroom in Japan, and then a kid puts a toy in Ruby's gripper in here, and then it's an apple, and then the robot in Japan says apple to the kids that are in the classroom. So it's like a social network of robots, or a network of social robots for children. Yeah.
But I guess, Mohsen, I did have a question about the meta, not exactly the algorithms you've worked with, but if you wanted to take Ruby to 1,000 users, what would your recommendations be?
He has a long list.
Yeah, there's so many things that we would change on this Ruby. The hardware is pretty nice because the face is animated and it has so many degrees of freedom. It can do different things, but we definitely would have much less trouble if we were using a already made platform that somebody else created. But that's also tricky because usually those are small and tiny, and kids are not very eager to engage with them. This one is pretty large. Usually kids go on the back and hop on it or hug it from the front or touch the arms. They're not afraid of Ruby. But if anything, I wanted to change, the first thing would be the arms, to build or to actually buy some pre-built arms. It doesn't matter if it's expensive, but it reduces the effort so much. I can give you a long list.
That would be really handy.
Yes.
When you collected your germs data, I guess Ruby was already applying her own policy. So can people take this data and how can they apply their own policies or learn new policies?
So the way that Ruby actually collected data is it collected all the data from the rotation. So it allowed you to simulate different actions. So when you have all the views from this action, you can actually simulate different policies. So you can start from any one that you want and then explore as you wish. So it collected exhaustively all the views of all the images to allow simulation of different policies.
Okay, again, 6:30 tonight, if you want to come celebrate. I assume we're going to be celebrating. We'll see what happens next. And we'll have my famous cashew chili. The champagne will be cold and the hot tub will be hot. So, thanks everyone. Thank you. Okay, and we have to kick you guys out.
Was UO planned, Mohsen?
So dynamic.
No.
Grab a cookie.
Thank you for fabulous.
Thanks for coming.
I just happened to be here for these 2 days. I'm so lucky that I was here. I won't see you tonight, and so I'm going to make you. That was a beautiful story. Okay, I'll catch you later.
How's your wrist?
Huh?
How's your wrist?
It's getting better. Still not functional.
It's a pocket analog. Technology schools.
Anna, are you here for the IBM thing?
No, unfortunately not. I'm flying outside.
Good job.
No, I mean, were you here for the IBM?
Oh, was I just, Javier, I was involved in it. And he said to give you hugs.
Oh.
From Javier.
The IBM's giving us $10 million. So,
Thank you.
Andrew was involved.
Oh, and that was yesterday.
Yeah. But I'm not involved.
Yeah, I'm not involved in that one, so. I won't see you tonight. I know. So I was just going to say, nice to see you, and I'm sorry I didn't get to see you more. I was just dealing with the 2 days.
One robot that we know of.
Aren't you finished yesterday? So we're going to be celebrating 2 PhDs.
I think some Joy left.
Hello. Good, how are you? Are you?
Okay. Sean-Joy, do you have some questions or?
He actually left and sent me an email and said, great job.
Oh, okay.
So just one question. One technical and one two questions. One technical, one technical. So technical questions in terms of last piece, sounds like AlphaGo, really overwhelming strategy is to have the policy knowledge and also value knowledge, right, to guide. As long as the search space is big enough.
Yes.
So what do you think is like to apply those type of strategies?
I actually would like to try something that is actually, I think it might be a problem, is that this is really a fine-grained visual categorization, So AlphaGo uses image processing, but it's not really an image recognition. It's a fixed board. But the way that they overwhelmingly use different strategies like the supervised learning and the Q learning, that's actually pretty nice. I think the next step would be to learn the supervised thing and then fine-tune it using Q learning, things like that. But yeah, I think that would be very interesting, especially with the shift of attention thing. I would like to try that and see how it works.
So my non-technical, so which one is your fiance? So there are 2 girls.
Oh, the first one. She was here sitting the first seat there. But yeah, the 2 are the undergrads that work in the Ruby project. Yeah.
So in a lot of your graphs, what I was a bit surprised was like, there was not a huge difference between like just random exploration or whatever and like the performance you were getting. Is this just because the action space is kind of limited and you got after 5 views or whatever you're gonna basically know it anyway, or?
Actually, the thing is that you see the thing. The thing is that the problem is not in the action space. The problem is in the transferring the knowledge from the good policies to the test time. So using this last approach where I extract some good policies on the training set, the difference is pretty huge actually. If I go using those ground truth or optimal policies, they do significantly better than random. But in learning those policies, it actually becomes very difficult.
So it means it's overfitting? Is the
Yes, those yeah, actually, basically it means overfitting. So there's not much work doing in supervised learning of policies that are already extracted. There's some exploration that need to be done in that. But as we learn those policies better and better, this gap becomes larger. So the good property of this work is that it gives us a higher, an upper bound on how much good we can do. And that upper bound is actually pretty higher than random. But we need to learn it, and that's not too easy. I've tried so much, but it's not easy yet.
And but the space of actions that you have here is basically just turning different. Like how many possibilities are there for the?
In this last work, there are only 5 actions. In the previous one, were 10 actions.
So what is your intuition if you like, if that space sort of grows exponentially. Or I mean, if you have like something that approaches, I don't know, like even a continuous space or something like that. Where it's like
The action space.
right.
Yes, again, it falls into the PondDB literature. And again, um, they have very much difficulty in going to continuous space of actions and continuous space of observations. I actually found this belief tree search after going over so many works, but when it goes to continuous actions and to continuous observations, it becomes very difficult to get something that has some guarantee of optimality. The things that we have currently are only on discrete actions and discrete observations.
And why is that? What's is this like again? Is it just like overfitting, or is it like?
It's actually the theory is pretty complicated. I'm going from the discrete to the continuous space because the function that you're modeling is kind of unknown, and you're just providing like a lower bound on it, you're just pushing it up. But when you go to the continuous space, there's so many different, things that you can model. The space becomes super large. You only could just overfit to a specific problem and provide some guarantee on that. But yeah, again, there aren't many. I'm not an expert in the theory analysis part. What I found is that they're struggling pretty much with the continuous actions and continuous observations.
So very high level question. Then all this stuff with vision, and face recognition, expression recognition, active object recognition, and I'm just wondering how much of this would transfer if you wanted to. As I understand it, Ruby doesn't have much audio capability in the way of voice recognition, so you could recognize a child that was behind the platform, or speaker detection, or emotion detection. I mean, all these things. Audio is a big clue too. Would all this stuff kind of just transfer, or not that you're going to do it? But...
Yeah, actually, it could help. The problem is that we actually tried the voice recognition. It's very noisy in the classroom. That's the major problem that we're having. It's very noisy. And kids are crying, and there's toys going out loud, and there's something playing music. So it's the hard problem is on that side of the environment being noisy. But if that is somehow gone away or just removed or fixed, I think the voice recognition could be useful. They don't talk much, they just say like a word or two.
I think that's why you have to do something that hasn't been done, which is sort of active voice recognition.
Yes.
You need a lot of microphones in the same way they're doing for vision.
Actually, we thought about it, and we talked with people here in KIT about creating a microphone array. The major problem was that there aren't enough people on the Ruby project. It's just me and Ruby, and but definitely that's something that we thought about.
So all these times when Ruby was chiming in behind you, it was just based on vision?
Yes, actually, it's less than vision. It's just the sensor in here. That's an IR.
I see. Okay.
Yeah, but
sometimes it had some eerie.
She's got some random
yes
movements there, basically.
Okay.
Yeah, so the randomness makes it not boring. If it's predictable, it becomes pretty boring very soon. So we have to put some randomness in the behavior.
So go ahead. Another question is like, so you started by motivating this by the, studying what kids do and whatever, but then you never got back to that.
Yes, that is one the major thing that we have. Again, going for a robot to go in the classroom and in the real world and do interaction, we did that for the first 2 years, but at that time I wasn't doing serious research. There's the problem of timing, and again the force, the human force,
But is it because the technology is not good enough yet to be useful in that context, or is it because it's just a question of work?
I think that's the general trend in robotics, when they just develop for the lab and don't go into the classroom, don't go to the real world, So in case of the hardware, and there isn't enough push to make it actually resistant to the real world and to a kid that comes and punches or kicks. So we have to actually go for less than 2 years because kids that are larger will break the robot more often.
Yeah, this Ruby over here lasted how many days? And
I think that one lasted like 21 days.
21 days in the classroom autonomously before what they broke her arm.
Yeah, actually Ruby 5 lasted like 28 days, and I wasn't here in the country, and they broke the arm by twisting it too much. But it lasted 28 days, which was pretty significant, without any supervision. Yeah, it's a brutal work for.